Hello YouTube, iFixItAll here, Team iFixItAll. A few weeks ago we had a power outage and I was trying to keep my deep freezers running, and usually I use an inverter here in the garage and let the car idle to keep the deep freezes from losing our food. And I noticed the one of these plug-ins here had no power. I thought, oh my gosh, what's going on? Well, let's see. I think it's this plug. Yeah, doesn't matter. What mattered to me was during that outage, I was like, oh God, I'm probably never going to find this problem. If I do a visual inspection, I'll look around. So let's see if we can dive in and see what's going on. I'm going to remove screws everywhere I find them, and get the thing opened up, and let's have a look-see and see what's happening. Because if these are independent outputs with individual sources, then that means when I look at the circuit card in there, I'll see mirror images of circuitry. That will aid in troubleshooting, meaning I can power this thing up live. After I do, you always do a visual first. You open up and look. There's a visual. Use your senses. You can even use your nose. Does it smell like the pixies got out? Then you look around for things that look different. Darkening of components. You're looking for the circuit runs on the circuit board. Is there a path where electricity would flow that part of the solder path has exploded and obliterated? Or components that look like capacitors, they have the top have popped on the electrolytic capacitors and they're leaking electrolyte. You do a visual in detail. Sometimes it helps to have a magnifying glass. Voila, with a light. Visual first. Use your senses first. Because we have already used one of our senses to detect the reason why I'm doing this video. It don't work. No worky. Next question, why? It's not a crime to ask why. Okay? So here we go. We're going to open this puppy up. Hang tight. So I've got the screws out. Getting somewhere. Sorry about that. I had to fight this cover off. And do a visual. Look around. I'm going to get you set up to where you can zoom in with me. Okay. We're looking around. Turn this overhead light on. Looking for any objects that... I guess I should have discharged this thing. Let me, there's some capacitors in there that might be holding a charge. That should be long enough. Looking around in there for any burnt stuff, you know, as to, oh, wait a minute. Whoa, hang on. So check it out. I see this jumper, and that's from the bottom terminal. That's your my finger's too fat. That's your ground prong. Why are they jumpering the ground prong? Oh, there's a blue wire that goes from this outlet I don't know if it's okay to do that or not. Let's rotate it. I see what's going on. So you got a brown from this outlet, jumper to over to here, and a blue from this outlet plug, jumpering over to here. So brown is, this is all European color coded, by the way. This is not USA made, obviously. The Europeans use brown and blue, and then the yellow with a green stripe. Color coding for 120 volt outlets. Let's see what the hell this... Let's confirm that. This is a 1200 watt inverter. ETL. Made in Chinese, yeah. Risk of shock. Intertech. It's ETL listed. It's not UL. It is, it conforms to UL standard 548. I forget what ETL stands for, but if it was UL listed, it would say such. But 'tis not. Back to the outlet plugs. So what I've discovered is this is a single source where the DC power comes in with a red cable here and the black cable there because it's upside down, but it says input 12 volt DC, positive and negative. And then you got a chassis ground here. And then it not only steps the voltage up through several stages of transformers, it inverts it from flatline DC to alternating current, or AC, to power stuff, and to the tune of 1200 watts. And how many amps is that? It's easy to do. We have the P equals I times E. $1200 watts divided by 120 volt. 10 amps. Max. I would say that power would be pretty damn dirty if you max this out. It won't be clean AC sinusoidal waveform. Sine wave being if you draw a straight line, you go up and then down. 120 volt peak on the positive stroke, 120 volt peak on the negative stroke. But it looks like they shoot into the big tang on your outlet, the big opening is your neutral, and the little opening is your hot, and this is ground. If anybody wants to know what the difference is between the neutral and the ground, just message me. So the brown is hot. So they come in from here with the main 120 volts, this brown wire here. Travels up to an outlet. And this is the first outlet, and then everything's... Oh yeah. Okay, I see what's going on. These are just in parallel with each other. So it's a single source up to the outlets, and then they've daisy chained two outlets together to give you two outlets. These aren't two independent circuits in this entire inverter. By the way, this is a heat sink, and so is this. At least you would think it is. I can't see how that heat sink is tied to this. Kind of makes you wonder if it is or isn't. There is a fan. Checking the blades. See if there's any damaged blades. Fan really is performing well. I can tell by the way it's dingle-dongling. And bouncing. It's got the magnetic poles. It's not. It moves freely. Should check these connections while I'm in here. It's DC input. Make sure these terminals are... Oh, they just stacked them up on there. Then divided them up across these power transistors here. I'm not seeing anything obvious. I'm looking for areas that look dark. Oh, look how they take that DC input and they... Wow! Well, they got a crap ton of fuses right there. So yeah, when you hook up a big old battery cable, they come in here, and since current is additive in parallel, since there's not a fuse, since it would be cost prohibitive to use one big fuse for your DC hot input, they spread that current across several fuses and solder them right into the board. And these are 30s, so you got 1, 2, 3, 4, 5, 150 amps worth. Well, what is 1200 watts at 150 amps? So we got 1200 watts divided by 12 volt DC is 100 amps. So, but to size your fuse, generally you want to do times 1.5 or 1.3, somewhere in that range, because fuses aren't, for the most part, calibrated to below exactly at the same ampacity as another fuse. It might be 5 or 10% difference due to metallurgy and manufacture and machining and all of that. The elements within a fuse, no two fuses will blow at the same amperage. However, you can pay for fuses that are calibrated to do such. So we have 1200 watt inverter divided by nominal 12 volt is 100 amps, but you need to add a little headroom to that fuse to offset for inrush and all of that for when this thing is powered up or it's overloaded. You size your fuse by going times 1.3. That's 130 amps. A lot of engineers take 100 amps and they'll divide by 1.33. Oops. 100 amps times 1.3 is 130. I wonder why they went 150 on that. I bet they used 10 volts. In other words, while you're using the inverter, this inverter will operate to a point where your battery voltage probably gets down to like 10 volts DC, so that's easy. 1200 watts divided by 10 is 120 times 1.3, 156. They just said screw it. Yeah, so as your voltage goes down, your current demand is going to go up, because nothing's going to stop your device from drawing the wattage it needs except for a low potential. And when your potential gets low and your current goes up, that's when things start smoke checking. You start approaching a direct short. So now we know that there aren't two duplicated circuits in here, that it's just one circuit. You got one conversion, you got one DC input going through all this rigmarole and showing up as one output, which is a single blue lead. Boys, I just think we found our problem. Well, let me finish my statement. A single blue, a single brown, and a single yellow/green, and then they're paralleled up here. Just found the problem. Let's zoom in. See if I can't get my fat fingers involved here. Bending. Check this out. Well, that answers as to why that one outlet wasn't even working. It wasn't even making contact. Let's check them all. Well, it looks like this. There's a green coming into this terminal right here, green-yellow, or yellow-green. That terminal's real low, and this one over here is real high. Oh. This is all jacked up. I'm looking at it a lot better than what you can see right now. But I can tell right now these connectors, the plastic, the plastic molding that this metal terminal depends on to keep the metal terminal in place. There's a little tab right here. The plastic seems to be missing. Like the act of me plugging something in pushes the terminals away. Hang tight. Actually, I was going to plug something in to show you that it's moving, but it's obvious it's not. Alright, so here, guys, what I'm going to do to fix this, I'm going to epoxy this. I'm not going to let you guys sit around and watch this. Turned out to be pretty boring, but that was the fault with this, was the terminals here. I honestly, outlets hardly, I don't know, I mean, outlets hardly ever fail. I mean, we just genuinely think of them as, well, they've almost got to explode to fail. To me, you're looking for a metal oxide varistor, some sort of semiconductor, a diode, a capacitor. In this case, I was looking for a capacitor, a resistor that was shot, something else in here that gave you a visual indication that it's kaput. But this one turned out to be a simple fix. Alright, so what I'm going to do is on the back shell of these outlets, I'm going to study where it is best to add some JB weld. And add little dabs of JB weld. I'm suspecting most likely I'll pile up JB weld on this side right here. I will JB weld all of these tabs and let it set to the side. Alright guys, that's the end of this video. I'm going to move on. We shall see you. Bye.